I'm actually going to jump over to the flip chart real quick. Got this keyed up because I can draw on it. Betcha. Here we go. Okay. So here's what he saw. We saw the gas make different colors of light, but they were really, if you look at hydrogen, it makes these really particular, it makes that red, a cyan, an indigo, and there's a really deep violet that's in there as well. So the question Bohr was solving was like, how, why, what's going on? Here's what's happening. Draw this out. You got your diagram on the bottom? Draw this out with me. So we'll do the red one first. So we could imagine that electron, okay, do you see the atom here?
Yeah.
Hydrogen atom, we'll label it. This is a hydrogen atom. What part is in the middle here? Yeah, so here's our nucleus, and then here's the electron. I'm going to label it electron with an E minus, and the little minus kind of goes up top. That's going to be our abbreviation for electrons from now on. Lowercase e with a little minus above it. That's our electron. The electron's just whizzing around. It's down on its base, its ground state, which is like the lowest possible. It wants to be down low. It's like the lowest energy level. This hydrogen atom is part of this gas tube. It's one of many, many, many atoms. It's just hanging out. I flipped the switch on my electricity thing, and we blast a ton of electricity through there, and that electron is now getting hit with energy, right? And so the electron can't stay there. It gets hit with energy. It wants to, it gets excited, and so it jumps up to the next level. Okay? It jumps up to the next level for a moment. It has more energy. It's an excited state. So this was our ground state, and it gets excited. It can't stay up there forever, though. It pretty quickly, kind of immediately falls back down. This rise up was an absorption of energy. As it falls down, it has to give off energy. It falls back down. As it falls down, though, it gives off an energy in the form of light. It gives off energy in the form of light. Wait, what causes the different colors of light again?
Different
Wavelengths. And how do we make different wavelengths?
different amounts of energy.
Yeah. If I measured the wavelength of the light coming off, could I therefore back calculate how much energy that must have been?
Mm-hmm.
Oh, that's what Bohr did. And he goes, oh, the reason we get this really particular and only this one exact red wavelength is because that's the energy of this drop.
Kind of weird.
All of these atoms of hydrogen are having their electrons drop the same, we could call it a distance if we want to be simplified with things. They're all following that same distance, giving off this type of red light. We don't see any electrons following these other colors, these other distances. They don't exist for this hydrogen. But then we get to cyan, and we go, oh, maybe the electron could jump and skip a row, and then as it falls back, it gives off, notice I try to drive my wavelength a little shorter. My lines are closer together, my squiggles. And that would be this possibility. And then there's even there's a higher level. I haven't drawn all the circles that are possible here. So there, our note to that would be the different colors are caused by the electron's energy drop. You'll notice there's really particular possibilities for the electron. It's not, and this is the weird thing about electrons. They can zip between levels, but they'll never be halfway. And what's wild too is we've measured this zip, the transfer between this, it doesn't take time, it's actually instantaneous. It's like a teleportation, just bang. It's up higher, bang, it's right back down. It doesn't go like, boom, boom. It's just boom, from one to the other. It's wild. Electrons are bizarre. And so Niels Bohr in like 1911 or 1913, looks at these color evidences, calculates how much energy that must be, and using that realizes that these electrons are stuck on these levels. And that explains a whole lot of things that they were looking at and wondering about. Cool? Can I connect this to astronomy super fast?
Yeah.
Okay, so if this part is confusing, that's okay. I'm going to go really fast though. The opposite of this is also true. When you shine all the colors at helium, we'll start with hydrogen. When you shine all the colors of light at hydrogen gas, the electrons want to absorb that light if they can, but they can only absorb the colors of light that correspond to a rise for them. So is there a possibility, is there an electron jump that corresponds to the energy of yellow light for hydrogen?
No.
No, but there is for this really particular red, this cyan, and this indigo. So if you shine all the colors through a cloud of hydrogen gas, you get what's called, instead of an emission spectrum, you get what's called an absorption spectrum. Well, yeah, I'll just do
Hydrogen.
absorption spectrum. And these absorption spectrums are unique for every element. And what it is, here's like all the colors, right? The emission spectrum. And then the absorption spectrum is you will see there will be little tiny missing colors that don't make it through the cloud of gas. Why don't those colors get through the cloud of gas?
They get absorbed by the electron?
Yeah, and what's kind of wild is that every element has its own unique colors that it absorbs because it has its own unique arrangement of electrons. And so, oh wait, could I look at the light coming through a nebula? Nebula are like hundreds of, like thousands and thousands of light years away. Could I look at the light coming through that nebula, see that it's missing really particular colors, and therefore deduce what the gas cloud in space is made of?
Yes.
Holy snap, like that's crazy. We can do that more locally. We can look at Jupiter, and we can see the light that bounces back to us off of Jupiter, and see that there are missing colors, and we can measure the atmosphere of Jupiter from here.
But how can you tell the colors of the sun?
So you take the color that's coming in, through the telescope, right?
Mm.
And you literally use a prism. Like the original measurements, put a prism on the telescope. And so it'd be like the star, and then right next to the star they would make that like our glasses did. But they did it a little more carefully. Instead of like all 8 directions, they would just go one direction, and they could look and they would see what the lines are. Now, we have much more sophisticated optics that will use like a computer sensor that will be able to give us like number outputs for like the individual wavelengths and how much each one is missing and the percentages and big calculations. But the fundamental, like the basics of it is this. It's awesome. I think that's super cool. We can like study the universe from here without being able to leave here. We can like know stuff. Okay, that's super cool. That's the light notes. Are there any questions? We're going to take like a 2-minute stretch break. When we come back, we'll be working on lesson 11. Thank you very much, everybody. You're awesome. Take a stretch break. Lee, hit that thing.
What's the time?